All right. So yeah, I got 5:35. So let's get started with the second to last lecture. So we're here August 14th. We're through templates. Well, basically through templates. We're going to finish it up today. And then next, hopefully I actually do want to get through exceptions and the STL today, or at least a good chunk of it. And then on Wednesday's class, we can finish up and then go into final exam review. So the final exam is the 19th, although please do double check. Yeah, so everything's wrapping up rather quickly. So yeah, small group today, I guess. Well, it could be a variety of reasons. Of course, one reason might be that assignment 4 is actually due tonight due to some VPN issues over the weekend. But yeah, I think that's yeah. Any questions before we get started? Okay. Just I mean, it's a pretty small sample size, but just out of curiosity, if you were taking this class again, let's say, you know, we go back in time, how many would like it as a half summer course as opposed to a full summer? Or do you like the full summer? Or you don't? You like the full summer? Yeah. You like it spread out a little more? And okay. All right. So I'm just thinking about next year and what the options will be. Full summer's better. Yeah. Yeah. I think it's half summer would be very hectic, but then you get, of course, half your summer off. But all right. Good. I'll take that into consideration for sure. Okay, so last class we were talking about templates, and we had come to let's go back here. And then we had arrived at the vector class. So the vector is part of the standard template library, and it is a templated class or a class template, which means that you know, it doesn't actually exist as a class until you declare it using some type. So we were going to take a brief look at it and just see some of the ins and outs. It's going to come under a lot more focus when we get to the STL, and there's of course a few I guess questions on the exam. Of course, if we don't get to the material, any material that you see in the exam, because the exam's already submitted, and if we don't get to that part in class, then those will be bonus, and they will be I will let you know which questions they are if that happens. But yeah, we wanted to talk a little bit about vectors. Since we've learned how to make our own templates, we can now take a look a little closer at how vector works. So what we're going to do is we're going to make a bunch of student objects. We have a student class here, and I've, you know, overloaded this operator, and we might overload some other operators. And then I make a vector of student pointers. And then what we're going to do is so this vector has these two functions, capacity and size, that tell us some of the values associated with our vector. In particular, so a vector, as I probably mentioned before, has a backing array. So we made a bunch of data structures that had backing arrays, you know, scene array and what was the other one? Video array, right? So those are classes, but in behind the scenes, you have a array of whatever it is we're going to store, either scene pointers or video pointers. And vector does a similar thing, except the thing about vector, probably we've mentioned this before, but it does grow and it doesn't shrink. It will only grow, but once it fills up, when you add more things, it will destroy, well, it'll make a new backing array that's twice the size of the old one. It'll copy everything over and it'll destroy the old backing array. So that way you in some sense never run out of room in your vector unless you run out of memory. So yeah, what we're going to do is The vector has a member function called capacity that tells you how big that backing array is. And it also has a member function called size that tells you how many elements are in it, right? So these are two different values. Our backing arrays had some fixed size, 256 or something like that. But as we'll see, the vector class is a little more variable than that. Okay, so we call the constructor a bunch of times when we make our students, Matilda, Joe, Timmy, Jimmy. And then when we first declare our vector, there's nothing in it. And our capacity is 0 and our size is 0. So if there's, if a vector holds nothing, then there's no backing array whatsoever. Next, we add Matilda. We declare that we're adding Matilda, and then we check the size and the capacity again. We have a capacity of 1 and a size of 1. So it makes a new backing array that has size 1, and it adds that new student to it. And then we can add another student here, Joe. And at that point, size of 2, capacity of 2. So this is, it appears that we're growing exactly as much as we need to, but what's actually happening is that this thing is doubling in size every time, as we'll see shortly. So once we add the third student, now our capacity is 4, right? So it doubled in size. It made a new backing array that was size 4. It copied everything over, destroyed the old backing array. And if we add 2 more things to our vector, then it should have size 8, right? So I'll have 4 and a capacity of 4, which is fine. And then it'll add the 5th, and it'll have to double in size again. And we end up with a capacity of 8, right? So vector it has a backing array the same as we had in our data structures, but the vector does grow as needed. Never shrinks though. You can tell it to shrink, but it does not take it upon itself to shrink, no matter how many things we remove from the vector. Okay, so that brings us to, we've added all of these students to the vector. What we can do is we can print out these students simply by making a for loop, right? That indexes itself from 0 up to the size of the vector. And then we can use the subscript operator here, which returns whatever's being stored there. What's being stored there is a student pointer. So we're going to have to dereference that in order to print it out. So let's see what that looks like. Okay, so need a little more space to get the proper formatting. So there's our students printed out using our vector. So we might be tempted to do something like this as well, which in this case will work, but let's get rid of this for now. Now we can see we got a problem. So not here. Oops, I did the wrong one. Sorry. That's not the one we want. We wanted, oh yeah, that's okay. No, sorry, I want to go here. So I have this global function, and I'm just going to comment that out. All right, so now we can see that I just took the entire vector and I sent it to the output stream, and the vector class does not know how to write itself to the output stream. Right? Not by default, because it's a class template, and it doesn't know what type of values I'm going to be storing, so it doesn't know how to print them properly, right? We can write a for loop here because we know that we're storing student pointers. We know we have to dereference them, and we know we've overloaded this stream insertion operator for the student class, so we know this will work. But as far as the vector is concerned, it has no idea how to print whatever you're storing in it, because it doesn't know what you're going to store in it. So when you're using a vector, a class like the vector, that is a templated class, what you often want to do, in this case, we know we're storing student pointers. So I'm going to overload the stream insertion operator as a global function, but I'm going to do it, instead of making this a templated function, I'm just going to say, well, this prints students. Students, it's going to print a vector full of student pointers, and I know how to print the students in that vector. This should be OST. And then I can, so for templated classes like the vector and other classes in your standard template library, you don't get this function for free. You have to write it yourself, but that's sort of, when you think about it, that kind of makes sense. Okay, so now my students get printed out using their overloaded operator for the stream insertion. See, questions so far? Okay. All right, so that's all fine and good. We're going to make another vector of student pointers, and we're going to use the vectors copy constructor. Okay, so we're going to pass in COMP2404. We're going to make a new vector called COMP2406. And we're going to take a look at some of the things that happen. So the first thing we're going to look at is the capacity. At this point, COMP2404 should have a capacity of 8, and we will see what happens with COMP2406. Okay, so COMP2404 has a capacity of 8 because we added 5 students and it doubled in size each time. But when we copied it over, COMP2406 only has a capacity of 5. So when it made the new vector, it only made the backing array as big as it needed to be. Okay. Vector does overload, so we don't get the stream insertion operator for free, but we do get this overloaded double equals operator. And what that'll do is it'll go through and check the first location of vector 2404 against the first location of vector 2406. And all it's going to do is sort of recursively apply this equal to. And so when we ask if these two vectors are equal, it says yes. And you would hope that would be the case, since 2406 is just a copy of 2404. Even though the capacity is different, in order for two vectors to be equal, all it has to do is hold a bunch of items that are equal and in the same order. Okay. Yeah, so we can take COMP2406. We're going to push Jimmy onto the back of 2406 and then ask if they're equal again. And then we'll come back to this. Okay, so after we push Jimmy on, the vectors are no longer equal, which is exactly what we would expect to have happen. We can pop Jimmy off, at which point they should be equal again. Right, so after Jimmy's popped off, they're back to being equal. So it really is just a comparison of the items that are being held in each of the vectors. But we'll notice another funny thing about if we check the capacities again. So now I've put Jimmy on the vector 2406 and I've popped Jimmy off. But the vector had capacity 5 and I'm adding a 6th student. So what has to happen is 2406, since it didn't have enough room to store Jimmy, it doubled in size from 5 to 10 now. Right, so it's still going to double every time we fill it up, but it doesn't necessarily go in the sort of canonical order of 0, 1, 2, 4, 8, 16. If I initiate a vector with a different initial capacity, it's just going to double whatever value it had. Okay. Sort. Yeah, we'll get to sort. Okay. I think that's good enough for our introduction to vector. Just the way it grows, the way it can be, you can compare two vectors. Yeah, we're going to come back to vector when we get to the standard template library, and we're going to see some of these algorithms. You may have noticed a sort function here. This is part of the algorithms library from the STL. We're going to see how exactly that works when we get to iterators, because it uses iterators in order to, know what to sort. But yeah, so any questions on any of that? Okay. All right, so that brings us to the end of the STL. These are pretty important facts as well, although I do think we covered them before, but you can use the subscript operator to return something from a vector, but it doesn't do bounds checking. Or you can use the @ function, which does do bounds checking. And if you try to access something out of bounds, it will throw an exception. So often that is @ is probably what you want to use. Vector does have a copy constructor. However, of course, we were storing pointers in our vectors, so it's not doing a deep copy, right? Again, the same way we had to take it on ourselves to overload the stream insertion operator. If you want to do a deep copy of a vector, you would have to write that yourself. When we made 2406 out of 2404, it copied the student pointer addresses. That's it. Or not the pointer addresses, but just the pointers themselves. So there is still only one copy of each student in memory. It just had two separate pointers to it. All right, so smart pointers. Unfortunately, I'll come back to that if we get through a lot of material and have time. But it's sort of interesting, but not. It won't be on exam, so you don't have to worry about it from that perspective. It is kind of cool though to make our own smart pointers. Okay, so that brings us up to exception handling, which just let me get set up here a little bit. Okay, so exceptions is another thing that unfortunately we don't see on an assignment, but you will see some questions on the final, so it's good to know how they work. And of course, if you ever end up programming in C++, you will definitely need to know how they work. So first, we're going to start by talking a little bit about the difference between a fault and an exception, and then we're going to look at basic error handling. And then we will look specifically at exception handling and the consequences of exception handling. So the thing that's sort of unique about exception handling, the thing that makes it sort of useful is that it abandons the old sort of path of your program for a new path. But that also makes it a little bit dangerous to use, especially when we're managing our own memory. We have to make sure to close all the resources that would otherwise not be closed, right? So that's what's known as stack unwinding. When we throw an exception, the stack unwinds until we find a catch block, at which point the program resumes, but we popped a lot of stuff off the stack. Some of it might have been important. So we'll talk a little bit about that. All right, so no program is perfect, as you very well know, and if you're writing in C++, you definitely have experienced with programs not working. Any program of reasonable size has bugs. So a bug is just an implementation error. It's really almost impossible to not have bugs if you have, a sufficiently complex program. It's very difficult to anticipate all the things that could happen. And it's very difficult, especially when you start interacting with other code, then the things that can go wrong start to balloon. So your code's robustness is the ability of your program to handle faults or exceptions and keep running in a reasonable way, a useful way, right? So a fault is a defect or a bug or something that causes your program to crash. An exception is sort of by definition an event that's outside of what you expected to have happen. Maybe you tried to write to disk and the disk failed. It doesn't have to be so dramatic, but and there is some overlap with faults and exceptions, but generally speaking, a fault is you wrote a bug into the code. An exception is I anticipate something could have gone wrong here, maybe through user input or whatever. So I write an exception handling code. So types of faults, you could have bad input, wrong data type, unexpected format. These are faults or exceptions. Network failure, things like that. Software bugs, array out of bounds, errors, segmentation fault, null pointers, all of those fun things. So we try and write software in a way that minimizes the number of faults. And C++ is particularly, full of pitfalls. So good design sort of helps you to avoid these faults. When you have a bunch of classes with narrow scope, it's easier to debug them and then put them together, and then hopefully some of that has become clear. Code reviews, it's good to have somebody else look at your code. Yeah, I guess we didn't. I mean, yeah, really don't mind if you look at each other's code. You got to, as long as you write your own, but if you help other people debug, it's kind of okay. But yeah, what can happen is your brain fills in details. I thought I did this, and every time I look at it, it seems like it's correct, but then somebody else looks at it and says, oh no, look, you did something wrong here. So code reviews are one way to, prevent faults. Testing is, of course, a big part of a software engineer's job. So unit testing, that's similar to our tutorials, did little tests. Integration testing would be sort of the tests that are run, when we put all that together for the assignments. And systems testing would be, something sort of bigger than that when I integrate it with an outside system that I expect it to run on. So we want to discover faults before the user does. Oh my God, these just go on and on. Yeah, so anyway, testing is part of the software development lifecycle. So we usually use a planned systematic approach. Once that systematic approach has failed, right? So we tested all of our stuff, everything worked, we put it together and we sent it out into the field, and then some bugs started appearing, at which point we're going to be doing debugging. Right, so use the debugger if you learn how to use that. I'm sort of jealous. I never got to, I don't know, it's too lazy, I guess. But print statements work as well. You just really want to see the state of your program at a certain point, and print statements and the debugger both do that. But yeah, this is sort of the not planned part. Beta testing is a good way to find bugs, right? When I send out the assignment spec, a lot of people look at it, and if there's something wrong, I'm definitely going to hear about it. So yeah, it is useful to do that. So when we're testing, we want to do things like assume that everything goes right. Your data is, you just send in good data, users use your software properly. You want to make sure that things are working as planned, but you also want to make your code a little bit robust. You want to assume things go wrong, and when things go wrong, how are you going to handle it? So you want to test those paths as well. So yeah, debugging this, I almost want to bring this into the beginning of the course, but we'll look at it here today. But debugging is not guesswork, right? So probably a lot of you have gotten a lot more experienced at debugging. The first thing you want to do is find out exactly where it is crashing. So the not nice thing about C++ is sometimes where it's crashing is not where things have gone wrong, because you've corrupted it somewhere else, but it's a good start. C++, sometimes it works, sometimes it crashes. Then you have to look at things like, are you accessing bad memory? Have you deleted something, but you still try and use the pointer? Because sometimes it'll work. Did you initialize your variables? Because sometimes it'll work if you don't. But then other times, if there's garbage there, it'll stop working. Yeah, so once you know exactly where the problem is, then you can sort of narrow down what the problem might be coming from. Yeah. Okay, so basically how we keep our code robust is we do inline error checking, right? So in our code, we're going to say, well, did this error flag get tripped, or does this value make sense? Is this in the correct range? And then we're going to also, well, we're not going to implement it ourselves in our assignment, but there's also exception handling, right? So when something outside of those simple error checks goes wrong, I will introduce exception and try and handle it in a way that, we want to try and rejoin the normal flow of control. But if we can't do that, sometimes it's better to just crash rather than keep going and corrupt other data. All right, so I think this is, yeah. So inline error checking looks something like this. We do something and then we say, well, if whatever, if the index is less than or equal to 0, return false, something like that. This is good for simple error checking. We don't want too much in our code. We don't want, a bunch of if statements checking all the things that could go wrong, and then a little piece of code here, then that's kind of overkill. But, basic data sanitation is okay and encouraged. But that brings us to exception handling, where it's like, well, something went wrong. That's sort of, I don't know how to handle it inline and simply. So now I'm going to do something a little more drastic. And of course, when we handle exceptions, we have choices. We can allow things to continue. We can notify the user there is a problem and then continue. Really what we want to avoid doing though is corrupting the state, right? So if something goes wrong and it leaves our program in a state that we're not sure of, then we probably don't want to save that. We want to notify the user and say something went wrong and probably we're going to crash. Sometimes that's best. Okay. All right, exception handling is elegant because it separates error reporting from error handling, but it is slow and expensive, right? So it's not something, it's something went wrong. It's not going to be, it's going to slow your program down if you do this. All right, so the C++ library has an exception class. It is a base class of your user-defined exception classes. I believe it's a abstract class. I have to double check that, but it's very simple. It takes a string message as as an argument to its constructor. And then if you call the function what, that returns the message as a string. But in C++, of course, we don't have to use exceptions. We can throw anything we like. Right, so there is some argument to be made for consistency, that if you subclass exception, then, other people who try to catch exceptions will catch your exception. If I throw a number or a string, then maybe not. But yeah, so our try catch block looks something like this. If you've seen them in Java, you're probably familiar, but we have try. This is our try block. And inside the try block, we have a piece of code that might be, that might not be good. In this case, we're dividing two numbers and we want to make sure that the person's not trying to divide by 0. So we're going to check if the denominator is 0 or not. This is the error checking part. And then the error reporting is we will throw, in this case, a constant character array. And then the try block is always followed by the catch block. And yeah, so we catch the exception. In this case, we catch the constant character array and simply print it to the screen. But there are consequences for doing that. So we'll take a look at what those are. Okay, so I have three functions, func1, func2, func3, and very simple. I start in main. I have a try catch block, but we won't use it to start with. We're simply going to announce that we're calling function 1. We're going to call function 1. And then when we come back, we will announce that we've come back. Right? And so function 1 does the same thing, except it calls function 2. So it announces that it's calling function 2. It announces when it comes back from function 2, and in between it calls function 2. Function 2 does the same thing. It calls function 3, and function 3 says we've arrived in function 3, and then we're exiting function 3. And I throw an error in the a runtime error, but it's commented out right now. So we just want to see the flow of control from our program. So yes, this is P1. Okay, so calling function 1, calling function 2, calling function 3. So we sort of climb up the function call stack. And then finally we exit function 3 right after we land, and then we land back in function 2. And then we exit from function 2 and we land back in function 1. And then we exit from function 1 back to main. And then we're done. So this is the, traces the flow of control of our program. And so now in the middle of function 3, we're going to throw a runtime error. So yeah, base of all runtime error exceptions. And this is a concrete subclass of the exception class, I think, one of two only that are in C++. But so I'm going to throw this, and it's going to be caught by this catch block. But we're going to see that what happens is this stack unwinding. So calling function 1 from main, that's the same as up here. Calling function 2 from function 1, that's the same as up here. Calling function 3 from function 2. In function 3, and then this exception message, and we're done in main. So we're done in main is the same thing, but we've skipped all of these lines, right? So these are all, these are no longer executed when we throw this exception. So this is the part of, I mean, this is true in basically every language, but in C++, we have to, of course, pay special attention to this because we are managing our own memory primarily. Also in Java, you have a finally block. C++, we don't have that. So in Java, the finally block in a try catch will execute no matter what. So you can do things like close files or whatever you need to do. In C++, we have to sort of design our code well because we don't have that. So yeah, we started here. We called func1. Func1 called func2. Func2 called func3. Func3 threw an error, and then we went all the way back, and we picked up here. We started executing back at this line, and then we exited the catch block, and we executed this line. Okay, so that's all this example is for, is to make sure we understand the flow of control here and what's happening. Questions? All right, simple stuff so far. Oh, yeah. All right, let's do number 2. What did we want to show here? Yeah, okay. So this, again, number 2, we're going to look a little bit at the flow of control again. So we have this divide by 0 function that takes in 2 floats and returns a float. Basically, it just tries to divide the numerator by the denominator. But we do this check to see if the denominator is equal to 0. And if it is equal to 0, we throw this constant character array. All right. And then this catches a constant character array and prints it out. So let's run that. I think, yeah, it should be fine. So enter 2 numbers, 4 and 8. the result is 0.5, so it simply divided 4 by 8 and then says goodbye and we're out. If I run it again and I say 4 and 0, then it says instead of 0.5, it writes out divide by 0 error and does not write this goodbye part. Okay, so what happened in this case? Well, in the good case, and yeah, so here this is just a little bit of, I'm not even sure, we don't need this in here. We will just assume that the user is entering in numbers. I'm sure that's spam. Okay, so the user enters in 2 numbers. We try to execute this line, and at the end of this line, it says goodbye. So the first time we did it, we entered 2 numbers, 4 and 8. The result is 0.5. So this function returned 0.5. And then it said goodbye. So this executed. We skipped the catch block. We returned from here and we're done. But so it goes into divide by 0. It does take the result of dividing the numerator by the denominator and returns it successfully. When I throw this error instead, then it comes back here. This does not get executed. So what happens is this part gets executed, and then it tries to execute this, and it's going to take the result of this and apply it to the stream insertion operator, and then continue on down the line using chaining. But none of that happens, right? So all of that gets abandoned right in the middle of a statement in some sense, right? So this divide by 0, this stream insertion operator doesn't get executed, neither do these two. Instead, we get this error output, and yeah, that's it. So in that case, we avoided, because we threw it here, we avoided doing something potentially catastrophic. Of course, that changes, changes the execution of our try block a little bit. Yeah. Questions? All right. Okay. So yeah. So what happened? So in the first, see here if I can. In some sense, this might be beating a dead horse a little bit, but let's say in the first example, we had our main function. So we called that first, and then we had func1, and this goes on the function call stack. We had func2 and func3. And when things performed normally, we would go all the way up the function call stack, and then we would we would exit from function 3. This would get popped off. We would write a little something in function 2. That would get popped off. And then we would write a little something in function 1. That would get popped off. And then we're back in main. And we don't execute the catch block at all. On the other hand, let's just call this F1, F2, F3. If we throw an exception in this function, and we throw it, let's say we throw an exception out of here before we execute this cout line, then what happens is the compiler starts looking for a catch block, right? So I've thrown an exception. It looks in the F3 function. It does not find one, so this gets popped off the function call stack. Any code that did not get executed, that's too bad. Any temporary variables you had allocated there get deleted. It looks in the compiler, then looks in function 2. It does not find a catch block there, so it pops that off the call stack. Again, if there's temporary variables, they get deleted. Any code that hasn't executed does not get executed. It looks in function 1, it doesn't see it there. So it pops that off the function call stack. And finally, it finds a catch block in the main function. So it lands in the catch block in some sense and resumes the flow of control from there. And everything that was in F1, F2, and F3 is now gone, right? You can't go back and revisit those functions. They're popped off the function call stack for good. Yeah. And that is, let's get rid of that. Okay. So we can throw whatever we like, not just exceptions. You can even make a local variable, a local object, and throw it. The compiler will figure out how to optimize it properly, right? So it'll generally only make one copy in the function that has the catch block rather than two copies and copy one over. The same when we do return values. The compiler doesn't optimize much. Generally, it lets you do things like that, but in certain circumstances, it just makes sense to do it. There's no way it will slow down your program. It will only speed it up. So, yeah. So our try, throw, catch. Try is the block of potentially dangerous code. So something might go wrong here, and if it does, we want to try and handle it. What goes wrong might not be in the try block directly. Sometimes it's in a function that we call from within the try block. But yeah. Throw is we've detected something has gone wrong. So we're going to, pass the buck. We don't know how to handle it. We're not quite prepared for doing this. Not only that, we don't know, right? If I'm making a library for somebody else, I don't know if they're, I can try and write something to see out, but how do I know that this even has a console interface, right? It might have a GUI. Writing to see out does nothing. So in some cases, if I'm making a library, I don't really want to handle the errors. I want to say, well, whoever's using the library knows how to communicate with the user, knows if they want their program to crash or what have you. I'm just going to gather up some information in an exception and throw it, and you can figure out how to handle it. The catch block deals with the problem. It catches the exception, tries to figure out what went wrong. It always immediately follows the try block, right? So sort of like an if-else. And then after the catch block executes, then it just picks up where it starts executing the next line of code after the catch block. All right, so yeah, there's another example. So basically, when we throw an exception, the control is transferred to the catch block, and all of the intermediate code that's not executed just gets popped off the stack. Yeah, and this is what we mentioned earlier, how you don't even know how errors should be handled necessarily. Whoever's using your library might have a better idea. So throwing exceptions is often a good idea. Yeah, and this is what we talked about, how we put things on the stack frame, right? If we can think of this as we start with func on the stack frame, and then middle on the stack frame, and then divide. This divide throws a divided by 0 error, at which point we do what's called a stack unwinding, and the compiler goes down the function call stack until it finds a catch block, and everything above that function is just popped off and lost. Okay, so what are the consequences of doing this? Well, let's take a look at a couple. All right, so we have here a main function. In this main function, I declare this some name variable, and I give it a temporary value, and you'll see why in a second. And then I assign some name the value returned from enter name. So I want the user to enter their name. I'm going to grab that, but maybe something goes wrong there. But at any rate, I'm going to print it to the screen. In my enter name function, I have a try catch block. So I ask the user for a name. The user presumably gives me something, and then I'm going to call this check name function. This check name function is the dangerous piece of code. So if something goes wrong here, I'm going to catch the error. And well, what does the check name function check for? It checks to see if the user's name is Timmy, and then Timmy's trapped in a well. I don't know. It's an old trope, but all right. So that is, if everything goes right, then we get the user enters a name. It does some checks. We don't care, but it returns this name, and then we print out the name. So this is what will happen at a high level if things go correctly. CDP3. Bob, and Bob's name prints out. If I try Timmy, Timmy is trapped in a well, and Timmy's name still gets printed out. Okay, so I mean, nothing too outlandish happening here. I came in here, I entered Timmy. This calls check name. Check name says, if the name is Timmy, we're going to throw this exception. And this exception is caught immediately here. So check name doesn't really return any values for us or do anything sort of useful in that sense. After the catch block, it prints out the error, then it resumes execution. It returns S. So S had a name entered here, and that name was successfully returned, even though there was an error in between. And then we were able to print out Timmy. Okay, so that's one possibility. So we're just going to show you a couple things that can happen depending on how you, write your try catch block. None of these are necessarily right or wrong. They're just consequences. But yeah, questions so far? Okay. So now we're going to do things a little bit differently. Okay, so instead of having a check name function, there's a couple of changes here. So there's no check name function. We're just going to do the check, right, and enter name. Really, functionally, there's no difference. This could be check name. In fact, I'm not sure why we just don't do that. Just so we have the exact same setup as before, with a couple minor differences. Okay, so we'll just call check name here. All right. Okay, so I got Copilot on. Sweet. Okay, so the exact same setup as before. The difference is now I don't have a try catch block here, right? In the previous example, I had the try catch block around the check name function, and here I don't. I instead put the try block here, right? Because I'm calling this enter name function somewhere down the function call stack. Somebody might throw an exception, so I'm going to try and catch it here, just for fun. Okay, so let's run that piece of code. So enter name Bob. So it looks like no trouble here, and Bob is printed out. So this gets executed. I enter my name. I enter Bob's name. Bob's name is returned. It's assigned to some name. I print this out. I skip the catch block. I print out Bob's name. All right, so let's see what happens now when we put Timmy in there. So Timmy is trapped in a well, and the name now is Abracadabra. Right. So in name one, the name Timmy was successfully returned. We found an error. We caught it. We handled it. The flow of control picked up where it left off, and we ended up returning the name Timmy regardless. In this case, I throw Timmy is trapped in a well. There's no catch block here, so this function gets popped off the call stack. This return never gets executed. In fact, I just lose this information. So now also this line never gets executed. I just abandon this try block altogether. And then the error is caught here. We print out Timmy is trapped in the well, but the name is now abracadabra, which is the name we assigned it up here. So this line does not finish executing. Okay, so same piece of code, we just moved the try catch block somewhere else. But the consequences were, you know, I guess, remarkable enough that we made an example out of it. In one case, we successfully returned Timmy, and in the other case, we still have our untouched string. Okay, neither is right or wrong, but yeah, questions? All right, I think this is the same as what we just did. Yeah, it's the exact same thing. Okay, so that's one sort of consequence of try and catch. Here's another one. So we have our good old barnyard. We have a bunch of barnyard animals. They can all sing. So the birds say tweet, tweet. The chicken says cluck, and the cat says meow. Oh, yes, and the pig. So I'm going to make one of each animal. I'm going to add them to my barnyard vector. And then I'm going to do the barnyard harmony. They'll all sing, and then we'll delete them, and then we'll exit the farm. So this is if everything goes correctly. If everything goes correctly, we get our little barnyard harmony, and everybody's happy. Okay, so let's see now. We're going to say, well, pigs can't sing. Right, that's ridiculous. So I'm going to throw a pigs can't sing error. All right, so now in my barnyard harmony, something bad might happen when I call this function. So what I'm going to do is I'm going to put this entire for loop in a try catch block. Oh, all right, well, thank you. Okay. So turn that back on when we need it. Okay, so it set up the try catch block exactly as I was going to do it. So now I have the for loop. It's fully within this try block, and then the catch block catches some error message and prints it out to the screen. In this case, when the pig tries to sing, it's going to throw this exception. All right, so now our barnyard harmony, before all of the animals got to sing, but in this case, the chicken sings, and then the pig throws an exception, and this try block is abandoned along with this for loop, where the message is caught here, and then control resumes after the catch block. Right, so I do not finish executing this for loop in this case. So that's one option. But you know what? Even if pigs can't sing, maybe I want to finish my barnyard harmony. So what I'm going to do is, let's see here. I'm going to put the try catch block inside of the for loop. So this is terrible, terrible indentation. Okay, that looks sort of reasonable. So now inside my for loop, sorry. All right, so the for loop goes from here to here, and inside it is my complete try catch block. All right, so now when I try to execute my code, so chicken, you know, little red hen says cluck cluck. The pig throws an exception that is caught and handled, but then the barnyard harmony resumes. The cat says meow, the bird says tweet tweet, because it does pick up, right? It executes the error message, it picks up here, and then it gets to the end of this block and says, well, I'm just going to continue with my for loop. So again, not right, not wrong, but we have to pay attention to basically how we implement these try catch blocks and what sort of impact it's going to have on our code. So yeah, questions? All right. Nothing too mind-blowing here, but sort of important. Right. So we've looked at try catch with a single catch block, but we can have multiple catch blocks. And the compiler it starts looking for a catch block with a matching parameter, and it stops at the first catch block it finds with a matching parameter. So, and perhaps we don't know what's going to be thrown necessarily, or maybe there's a lot of things that can be thrown, and we want to catch anything that is thrown, then we can use a catch-all block. So if I use the ellipses, or however you say that, it will catch anything that is thrown. However, now if you use the catch-all, you cannot use the throw parameter. So I don't know if it's an exception or a constant character array or whatever, but I can do maybe some cleanup or something like that. Okay, so I have, again, I have this class hierarchy of animals, birds, chickens, cats, pigs. These are all empty classes because I really only care about the types. But yeah, bird is a subclass of animal and chicken is a subclass of bird. Everybody else is just a subclass of animal. So I declare 3 different objects here, a chicken, a cat, and a pig. And then I ask the user for their choice of activity. We're going to throw one of these animals. And then I have a try block, and inside my try block, I just take a look at, what the user wants to throw, and based on that, I throw one of these animals. If I don't recognize what they've put in, I just throw whatever, a constant character array, a string, right? So, and then after my try block, I have multiple catch blocks. Here I catch a chicken, here I catch a bird, and by reference, which is fine. I catch a cat, a pig, and this is the catch-all. If everything else fails and I get down to here, then anything I throw will get caught here, at which point I simply return. Okay, so let's give that a try, and then we'll talk about it a little bit. Oops. So activity, let's throw a bird. We get a bird alert, sweet. Pig, we get a pig alert. Walrus, walrus gets caught. Right, so when we selected walrus, we threw whatever, and this whatever got caught down here. And said we got caught something, so everything's working fine. But so I have a little note here, order is important. So yeah, what's the danger here? Or what do you guys think is the danger? So I'm throwing a bunch of stuff. It's in a class hierarchy. I have some catch blocks. The compiler finds the first one that matches and executes that. Right. So what happens if I do change the order here? What if I do this? Right. Yeah. So exactly right. The compiler starts looking, it goes down the stack or whatever, but in this case, we have a bunch of catch blocks. So it's going to look at them, but it looks at them in order, and it finds the first one that matches. And because of our inheritance class hierarchy, a chicken is a bird. So a chicken will get caught here, and this will never get executed. And actually, the compiler will warn you about that. It'll still let you do it, but it says exception of type chicken will be caught by earlier handler, right? So I can still run it. So if I throw a chicken, I get caught by the bird alert. So it still runs, it still executes, but you do get a warning. So yeah, do watch out for when you have a class hierarchy, when you have these is-a relationships, you have to be careful the order of your catch blocks. The other thing, which is, so I declare 3 different types of animals here. Here I just throw a bird. C++ is, I really find this annoying because if I throw just this, it thinks it's a type name, right? So when I declare a bird up here, if I say, then I don't put any brackets here. And in fact, I could, well, yeah, I don't put any brackets here. If I did something like this, bird, this is incredibly wasteful, but so yeah. If I just straight up declare something like this, then I don't put any brackets if I'm using the default constructor. But if I declare it like this, right? So I'm making a temporary bird object and I'm assigning it to this bird object, then I do have to put the brackets here. And it's the same, here I'm making a temporary bird object just on the fly and throwing it, and I do have to put the brackets here, even though it's only using the default constructor. Anyway, I just find that C++ it like changes its mind everywhere about whether you want brackets or not, but yeah. Yeah, it thinks it's a type. Yeah. I mean, I'm used to it now, but when I was starting, it was like, do I put brackets or not? And it's nice, if you're running it in VS Code, then it tells you. But if you're not, then you have all these problems. And yeah, anyway, just a small annoyance that I found, but you're right. If I just do this, it thinks it's a type, right? So this is, yeah. Type name is not allowed. All right. Questions, comments? Okay. So yes, the order matters. So this is one example. These make good final exam questions. Sorry, do you have a question? Yeah. Yeah. The character. So where did we do that? So this is what you mean? Okay, so in some sense, I'm throwing a string here, right? But it's not really a string. So if I wanted to catch a string, because this is actually a good question. So error. Actually, let's go to, yeah, let's do it here. So I'm going to throw a string, or sorry, I'm going to catch a string. And here I'm going to throw a constant character array. So if I go to enter a name, if I enter Tim, terminate called after throwing an instance of constant character pointer, basically. So what happens is that it didn't match this to this, because this is basically a string literal, and so it's not a string object, it's a piece of memory, like C, basically, how you would use a string in C. If I throw this, then I have to use sort of the C version of string, which is constant character pointer, right? So that's what C uses. It points to the beginning of an array, and then it reads off the array until it finds the end of the, end of array character, and then it stops, right? So that's basically, when I use this, say well, maybe I can catch, we can try it here, actually. It's possible that might work. No. Okay, so it still doesn't recognize it. So we do this all the time. If we have a function that takes a string, we pass in a string literal, and the compiler implicitly converts it for us. But here it doesn't, for whatever reason. So this is, we do this all the time, like I said, but it is a little bit of compiler magic going on behind the scenes. If I want it to get caught, I can throw a constant character array. I just have to cast it to a string. And then I can do that. Well, let's see. Yeah. The string constructor gets called for me if I cast it. So yeah, compiler magic. I could, so what you're saying is something like this, which would probably also work. I think that's what you meant. Yeah. That, I'm assuming, would also work. Yeah, so Timmy is trapped in the well. So either of those. Here I make a new string and I supply it with an argument. It's not a new, it's a statically allocated, but still a new string object. Or I can cast it and let the compiler do the work for me. Or I can throw string literals and just catch constant character arrays. But yeah, it's a good question. Other questions? All right. Yeah, so multiple catch blocks, again, this makes good, it's a very simple question, but it tests, sort of an important concept. So here, if I have a vehicle, that's the base class of car, aircraft, and boat, and Mazda is a derived class of car. Then if I have a try catch block that looks like this, everything is going to get caught here, because everything that I'm, if I throw a car, an aircraft, a boat, or a Mazda, that will all get caught in the first catch block. So yeah, we have to be careful of the order. If I leave this off, well, then now everything is in order. So let's say I throw a car, the car gets caught here. It does not get caught here because a Mazda is a car, but a car is not a Mazda necessarily, right? So the order around the hierarchy matters. And if I threw a Mazda specifically, well, then it will get caught here exactly as it should. So yeah, do be careful of that. On top of that, we can rethrow exceptions, right? So let's take a look at 644. So here's, the Timmy's in trouble again. So I have my check name function. In my check name function, I throw an exception. It gets caught way up here. So let's. Throw will always call terminate. Oh, did I do? Yeah, because I. That's weird. All right, let's try to. All right, so Bob works. Timmy terminated. Why is it terminating? Huh. I don't know. Let's. All right. All right. I'm not. Oh, yeah. Sorry. We're getting to that part a little bit later. All right. So this should work now. Oh yeah. I have to change the. Yeah. So that's a throw specifier, which is it's deprecated all for everything except for. Anyway, we're getting to that in a second. Okay, so Timmy's been kidnapped by a giant squid this time. Poor guy. All right, so as we know, we started the main function. We call the enter name function. The enter name function calls the check function. If we throw this, this does not get executed, but maybe we have some cleanup to do here after. So what we're going to do is we don't want to take control here, but we do want to temporarily take control. So what we're going to do is we're going to introduce a local catch block. And then we're going to cleaning up some stuff. And then after that, we're simply going to throw. All right, so we're going to rethrow this exception, cleaning up some stuff in enter name. And now when I enter Timmy, it gets caught here. I'm cleaning up some stuff. I rethrow the same error and I get, this same error message. Timmy's been kidnapped by a giant squid. I get the same abracadabra name. Everything's the same, except I just temporarily interrupted I just caught this and then rethrew the exception. I don't even have to put the name of the exception that I'm throwing. I could just put throw and it will rethrow the exception that was just caught, right? So nothing has changed. It still catches this help Timmy's been kidnapped by a giant squid exception, but I don't have to specify it. Or I can say, maybe I want to catch this and throw something else. I could say a whole new right. No one else needs to know about Timmy being in a giant squid or well or wherever he got off to. I can, throw a whole new error up to the main function. The main function catches it and executes it. So yeah, we can catch and rethrow errors or catch and throw new errors. We can even do, again, if we don't care what we're catching, we can catch it and throw it as an unnamed error. Right, and so yeah, this still gets to the top. I didn't know what I caught. I'm not able to use it, but I didn't care. I just wanted to clean up some stuff and then rethrow it. Okay, questions? All right. All right, I think we can get through stack unwinding. So all of this is to bring us to probably the most, right? We do have to be very careful of all of these things, but the most important thing, oh yeah, so this is what we saw. This is deprecated now, but of course you might see it at some point. So I could, or you used to be able to in C++, sort of if I wrote a function, I could say what that function was allowed to throw. So here I'm saying my function can throw an integer or an exception. Right? If I don't specify, then my function can throw whatever. If I have an empty throw clause like here, it may not throw anything. And that's the error that we saw earlier, right? So if I go back here and say throw and an empty throw clause, and this has to match, then I get that. Yeah, with the, oh, sorry, put this in the wrong place. Okay, so I get the warning, throw will always call terminate, because I said, you know, that this function was not allowed to throw anything. So all of that is deprecated except for this. I can declare my function does not throw any exceptions. But if I try to do, I could try and might let us get away with it. It used to give a warning. I think now it gives an error. So if I say we can only throw ints, yeah, so we no longer, it's no longer allowed. That's been removed from the language. Okay. All right, so stack unwinding. So all of this, you know, a lot of C++ has to do with managing our own memory, and exceptions are no exception. So stack unwinding is when an exception is thrown and the call stack is popped off down to the catch block, and a bunch of, you know, we skip a bunch of code. So the consequences of that is the local variables get destroyed, but return values are never returned, and any leftover lines of code are not executed, including a delete, right? So I could, if I dynamically declare some memory in a function, and then an exception is thrown before delete is called, then I have a memory leak, right? So yeah, and that's just an anecdote from my past. Yeah, sometimes you write stuff like that thinking it'll never actually execute, and then it does. So yeah, stack unwinding refers to how do I, as I come down the function call stack, there might be cleanup I have to do in each of them. As we talked about, you can, of course, catch the exception and do some cleanup, but there's a couple other, and yeah, sort of the most graceful one is to make everything an object. This is the resource acquisition is initialization model, where you tie all of your resources to the life of a statically allocated object, so that it's sort of, you know, once your object gets deleted, it's like a domino effect. 654. Okay, so before starting this final example, we'll take a break. We'll come back at about 7:05, finish this up, and then we will move on to what's the next one? Oh, the standard template library. And that should take us to the end of class. And then whatever if we don't finish everything today, we'll finish it on Wednesday. And then regardless, we'll have We might have some lecture on Wednesday, but if we get done everything today, then we'll just have a final exam review, because it's right, it's a double pass, but it's not, I'm not trying to, like, I don't want to freak anybody out or anything, because I'm not really trying to fail anybody. What I want is to avoid what happened last semester, where I marked the final exam and I see what you guys write, and I saw people pass my class, get even great marks in my class, but they don't know how to code, which that's sort of and so yeah, the double pass rule is to make sure that doesn't happen. If you're trying and you make mistakes, that's different, right? So I had somebody on the midterm, they just misunderstood a question, and they did perfectly on everything, but they lost a bunch of marks because they misunderstood the question. And clearly they knew how to code, but they just made a mistake. I would never fail you for that. Okay, I would still pass you. This is just to make sure that everybody that comes up to this class can write some C++ code. Maybe not perfect, but something. Anyway, so yeah, I'll see you at about 7:05. All right. So 7:06, I'll get back to it. So when we left off, we were talking about stack unwinding, which is basically, when we do all this damage from throwing an exception, how do we make sure that, how do we make sure that our resources are cleaned up? But specifically in this case, we're thinking a lot about memory management. So all right, so we have 3 different examples of potential ways to manage our memory. But first, let's take a look at what this program does. So we have this, we'll just ignore this error class for now. We have an initialize function, and we have a main function that calls initialize in our try block, and just a standard catch. In the initialize function, we're going to ask the user how many elements they want to make, all right? And we're just going to fill up an array with numbers. So we're going to make a dynamically allocated array of ints, and then we're going to fill it up with numbers that we get from the user, okay? And then if the user happens to enter something that's not a number, then we're going to throw an exception, right? So this is, right, we're trying to read from the keyboard into an integer in this statement. And if we enter a character, for instance, then it'll throw this flag, and this check will return true, and then we're going to exit. Right, so of course, and if we don't exit, we continue down here, and we print out all of the integers that we entered. And then the important part is that we clean up our memory. Okay, so in knowing what we know about the flow of control, if we do throw this, none of this gets executed, including this delete. So that's the problem we want to solve. We'll just run it really quickly first. To see, so we understand precisely what it does. So enter the number of elements, let's say 3, and enter the elements 1, 2, 3. And it says, I entered 1, 2, 3. So that's great. If I run it again, 3 and A, B, and C, then I get this bad error, bad input, right? So throws the exception, it gets caught up here. Everything looks fine, but if I do, right, so enter the number of elements 3, A, B, and C. I have a memory leak because that integer never got deleted. And if I enter the elements correctly, 1, 2, 3, then I don't have a memory leak. So it really is in this case that throwing this exception, although it's good because I don't want my this is going to end up in some state now that doesn't make sense. So I throw an exception, I exit this, but I have not deleted this array. So how can we make sure that this gets deleted? Well, we did see one version of it, so we're going to see three versions. One's terrible, one's sort of pretty good, and one's probably really good. Of course, the one thing we can do is, all right, so yeah, we'll start with the terrible one. What I'm going to do is I'm going to have this class called error. It is a friend of main because main is, this is just to make our life easier. But this error class is going to take as in its constructor, it's going to take a pointer to an int, right? Which is basically a pointer to an int array and a message. So down here I have, again, this is a pointer. It's going to point to an array and a message. And I'm going to, instead of catching this, I'm going to catch an error. And then I can say, print out the message. But the other thing I can do is call delete on error.toDelete. Okay, so now I'm throwing an error object, and in this error object, I'm going to pack this piece of this array that I have to delete. So here I'm going to throw error. And if I do throw this error, I want my array, and the message is bad input. Okay, so I'm going to grab a reference to this thing that should be deleted, and then in my catch block, I'm going to basically take apart this this error object and delete the things that need to be deleted and print the things that need to be printed. Oops. Okay, so 3, A, C. All right. Wow, it really doesn't like that. Mismatched free delete. Oh, did I write it wrong? Yes, I did. So this has to be, since it is a an array, I have to use the array delete. All right, so 3. So error bad input. However, no memory leaks because I did free everything. Okay, so that it works, which again, working code is the most important thing. It's terrible in that, well, first of all, I have to, well, I could put this maybe in the destructor of this error class. That might be a better design decision. But the other thing is, I have to, this will only work in this case for ints, right? I can maybe make a templated class as well. But it only works for ints. It only works for one array of integers. And if I happen to change, if I happen to maybe I have a string here and maybe I have a bunch of stuff that I need to be deleted, now I have to rewrite my error class in order to accommodate it. So this is bad encapsulation, right? And this is why we try to encapsulate things, is because if I make changes to this code now, I have to make changes to my error code. And I want to avoid making changes in more than one place as much as possible. I don't want to tie these things together. I might use the error class somewhere else, and it has dependencies over there. So this works, but it's bad design. All right, so let's do the same thing again. What did I do here? Oh yeah, so in this case, I did things a little bit differently. So I have this enter int function that I call. And in my enter int function, I take in the user's number, and then I look to see if this threw an error. And if it threw an error, then, or if it, tripped this flag, then I'm going to throw this error. And this will be caught up here. But in the meantime, down here, I want to catch it and clean up my memory. So it's possible that this There was a const. But actually, I don't even care what it is, right? So I can just put ... because all I want to do here is, well, if an error has been thrown, I want to delete my array. And again, I gotta make sure I do that correctly. I'm going to rethrow whatever error it was. I don't care. I don't need to know. I just need to clean up my own stuff here. Okay, so if I go to number 2, oops. Okay, so error bad input, but again, I have to valgrind that. And yeah, so I did manage to catch the error that was thrown, and I cleaned up my mess, and then I rethrew it, and I got this error bad input. So everything worked the way it was supposed to, and this is good design, right? So this is I'm not violating encapsulation. I don't need to know anything about the type of error that I'm catching. I'm just handling my own business in this function. I'm saying, if this throws some kind of, exception, then I need to delete my stuff. So that's exactly what I'm going to do. And then I'm going to let somebody else handle that exception. So yeah, that is a good design. But of course, the best design is if we want to link this dynamic memory to the life of an object. So when the stack is unwound and this initialize function is popped off the function call stack, any local variables are destroyed, right? So in this case, this size variable is destroyed. It doesn't cause a memory leak. This is not destroyed because when I use new, I'm basically saying I'm going to figure out, delete this. But if I tied the life of this to an object that I statically allocate, then when this is popped off, the destructor will be called, and I can delete this array. So I left it empty. All right. So we'll fill it in here. So this is, I'm going to make an int array class. So this is the same piece of code, works exactly the same way. But instead of declaring a raw array, I'm going to declare an int array class and make sure that it works exactly the same. So it's going to take a size variable, so that'll initialize it. I'm going to override the subscript operator so that this all works. And then in the destructor, I'm going to delete the dynamically allocated array. So I want something like this. Here, let's see. Yeah, sure. Okay, and private. So we need a size and a pointer to an array. So in here, I will say this size equals size, and my array equals new. Okay, so I have this structure, I have this backing array now that will hold these things. I just want to basically override the subscript operator, and then everything will be perfect. Index. So this should just return, and I'm not going to do any safety checks or anything. So we just want to demonstrate. So I'll just return the thing directly. And then the final thing we want to do is make sure that Copilot's not helping at all, eh? So yeah, we just want to make sure that this gets deleted. So this is instead of making sure that we remember to delete, we just put it in the destructor, and then we're going to declare this as a statically allocated oh yeah, this should return a reference. Yes. Okay. So we want to return, I was returning by value. And when you return by value, that's an R value. So you're not allowed to assign values to an R value. If I return this by reference, it returns the memory location in the array, and then I can assign it a value. Hopefully. Okay, so basically what I did is instead of using this raw array, I made a myArray class, but this myArray class behaves exactly like the array does. With the exception is if this function gets popped off the call stack, the destructor will get called and the memory will get cleaned up. Okay, so let's take a look. First of all, we'll make sure that it works. 3, 1, 2, 3. So far, so good. 3, A, B, C, error bad input. Okay, so let's make sure that yeah, so we still get this bad input and all heap blocks were freed. So this is the best way to handle memory, is to tie it. You just basically tie all your dynamic memory to the life of a statically allocated object, and then it sort of happens gracefully, gets deleted gracefully for you. All right, questions? Okay. So yeah, we're covering a lot of material, but so here's some examples if you need reminders when you're studying for your but yeah, these are basically the same examples, just a little bit harder to read, of the different ways that you can handle stack unwinding and deletion of those outstanding memory. All right, so moving right along. So that brings us to the standard template library. So this is the material that you need to finish tutorial 10. And I did send out an announcement to this effect, but I'll remind you, of course, because there is no tutorial this Wednesday, tutorial 10 is also a bonus. And what that means is that I don't really care which 9 tutorials you complete, but you only need to complete 9 to get your full 10%. And any tutorials you complete above that, you get whatever they're worth. And that is added to your assignment plus tutorial grade as long as it doesn't go over the allotted 45%. Right, so if you want to earn extra marks, you can do extra tutorials, and there's a chance to earn above what you would get. But yeah, this all right, so the standard template library. So you know, we associate it a lot with vectors because that's primarily what we use, but it also contains a lot of other stuff. So we're going to talk about iterators, containers, which are vectors and lists and things like that. And then there's also an algorithms library in the standard template library that does things like sorts our vectors for us, or well, we'll see some of the things. You can loop over everything and call some sort of function on it, or things like that. Let me just get out of here. It's 19. Whoops. Okay, that's good. And let me. All right, so as mentioned, it's a library of classes and algorithms that operate on those classes. They are templates, which, and in this case, there are a lot of collection classes. So it provides useful container classes and the member functions that go with them. So, the one we've seen so far is vector, and there's a lot of functions that you can call on vector. We've only seen a very small subset. So that's the good part. The bad part is iterators can be a little bit weird when you first start getting used to them. They're a bit non-intuitive and they seem sort of clunky. Of course, the other danger is that you might make a lot of copies of stuff. You got to be careful when you're dealing with objects. We've seen some of that with the vector class, but yeah, as long as you understand how the data structures work, then you're not in any danger of that. So there are three main types of containers in our standard template library. We have sequence containers, which is where everything is stored in a sequence, like a vector or a linked list, or any of the data structures that we've been using. There's also associative containers. These would be more like a map or a hash table or things like that. And then there's container adapters, which we did see when we made a stack out of a vector, when we were dealing with the private inheritance. So yeah, container adapters are similar to that, where we kind of want to restrict the functions that are available to be used. So yeah, we're going to take a quick look at that, probably not get too deep. Now there's iterators. So iterators are an implementation of the iterator design pattern. So these are one of the design patterns in the Gang of Fours book. And what they do is they allow access to container elements in a consistent way. So what does that mean? Well, in practice, what it means is they behave a lot like pointers, which means a lot of code that you write for pointers will also work on iterators, but there is a limit, of course. And then there are algorithms, which, right? So if you've written one sorting algorithm, you've written them all, basically. So you don't need to reinvent the wheel. A lot of these algorithms are well understood and they've been written for you using iterators. So yeah, we have algorithms. The algorithms operate on iterators, which is just an abstraction layer between the actual data and my algorithm. And the iterators act on the containers. So what the iterators do is they allow the containers and the algorithms to sort of be changed and evolve separately. So we'll just see what that means. We'll see how awkward they look. So yeah, we have a student class here. Right, nothing special, just a regular student class with a bunch of member variables. And then we're going to make a bunch of students, and we're going to make a vector of student objects this time. And we're going to push our students onto the vector of student objects. Let's see, what did I do here? So yeah, so we declare when we're in the constructor, we declare when we're in the copy constructor, and we declare when we're in the destructor, just so we can see the life cycle of these things. And these examples you may have seen before, but we will remind ourselves what they do. Okay, so let's see what happened. Probably more than I wanted to have happen at the moment. So let's just do it piece by piece so we understand what's going on. Okay, so I construct a bunch of students, and then when I leave main, these students are destroyed because they're all statically allocated. Okay, then I'm going to make a vector, and I'm going to push 4 students onto this vector. Okay, so again, here's the original students that I made. These are sitting on the function call stack in the main stack frame. When I push them onto the vector, a bunch of stuff starts happening. The copy constructor gets called for Matilda and Joe, and then Matilda again. Matilda gets destroyed. Stanley and Matilda get copied. Joe gets copied. Matilda and Joe are destroyed. So when we saw the vector example earlier today, we saw how that every time it fills up, it doubles in size, and then it copies the contents of the old array into the new array. When we use pointers, that's a very inexpensive procedure, right? So copying a pointer is just one trip on the address bus. But when I'm copying now full objects, there's a lot more stuff going on. So if I'm using a vector of objects, I'm destroying and making and copying a lot of objects as the vector grows. Students. And then when I leave, of course, each student is destroyed twice, once for their, right, this is a statically allocated vector of student objects. So these all get destroyed for us. So there's no memory leaks. Everything is good, but we're doing a lot of copying of data that we don't have to. All right, questions on that? Okay. And then of course, after we add them all, that's all fine. We can do that if we don't care about how expensive it is. There's nothing, we're not leaking memory and we're not really doing anything wrong other than we're being a little wasteful. But I can print out all my students on my vector using the subscript operator and the stream insertion operator. Okay, so my students all get printed out, or at least the 4 that I put on the vector. Okay, so that's the vector class. Maybe we want to, so there's also a list class in the standard template library. So I'm going to declare a list of students. This is a doubly linked list, right? So similar to the linked list we made, but this is doubly linked. And we're going to do the same thing we did earlier. We're going to push students onto the linked list, the same as we did with the vector. And let's see what happens. Okay, so when we pushed students onto the vector, we had a bunch of copies being made and students being destroyed. When we pushed them onto the list, we pushed 4 students onto the list, and the copy constructor was called once for each of those 4 students. So if I'm storing objects now, then the list seems to be more efficient in that I'm not making and destroying a bunch of students unnecessarily. It will grow as large as I need and never have to, destroy old stuff and make copies of it. So it's a lot more efficient in that way. So being a linked list, though, now how do we access things? So I can try and do the same thing that I did for my vector. Well, the vector has what's called random access, right? So the subscript, when I call subscript I, it jumps right to the ith location because it's just a backing array. And it returns that object and prints it. But for my linked list, of course, I can't do that. I got to start at the head and I got to walk down the linked list to location I and then grab that. So this random access does not work for this. Of course, we haven't seen it a lot. But we can do this. We can do, actually, I haven't used it at all, but there is a for each loop in C++, and that for each loop will work with these students, or with these lists. So I can say, well, for each student, make sure you use a reference here. I can print out stu. Yeah, okay. This is not iterators, by the way, but I figured I can show you the for each loop. What happens if I don't have this reference? Like, there's no errors being shown here. The compiler's still happy, but what do we think is going to happen? Yep. Yeah, exactly. So every time this is like, if I pass by value, it's going to make a copy of the student. So if I go into, so we can see, so yeah, I didn't really announce when I was printing my list. So pushing students onto the list, let's say, oh, okay, so I'm printing the list here, and every time I print off a student, the copy constructor is called, and then at the end of that loop, the destructor is called, and then the copy constructor, and then the destructor, copy constructor, destructor. Because yeah, every time it goes, this is in some sense a pass by value. So it makes a copy instead of using the student that instead of this being a reference to the student that already exists, it makes a copy and puts it in that variable. What's that? If I use what? Sorry. Oh, yeah, that's a good question. Yeah, that's another thing we haven't covered. We deliberately keep things low tech in here, but so we can auto. That's a good question. I'm guessing. No, it's still made copies, eh? Can I do that? So auto just, inspects whatever type is being supplied here and automatically generates the proper type here. It's still strongly typed in that you can't change the type of stew, even if you declare it using auto, but auto will let the compiler figure that out for you. But yeah, if I use auto, I still have to use the reference. Yeah, it's a good question. Yeah, other questions? Okay. So yeah, but that's just a for each loop. That is not using, uh, that's not using iterators yet. So yeah, this is just notes based on that. Basically a linked list. If I'm making if I want to store objects for whatever reason, then a linked list might be a better choice. It's kind of slow though. I mean, you can do benchmark tests on it. Vector is still, or array-based things are very fast because, well, there's a lot of tricks that they can do to copy them over, right? So it may not be, vector is sometimes still better than linked list, but so yeah, how we access things in a linked list or even in a vector using the standard template library is to use iterators. Now, iterators act a lot like a pointer. They are not a pointer, but syntactically, a lot of the same functions will work. So yeah, we can use them to traverse a container and as an argument to a standard template library algorithm. Let's see what we got here. So we have the same student class. Now we just have a list. So what we're going to do is we're going to grab an iterator into the student list. So list iterator. No, that's not what I wanted to do. Am I getting that wrong? I might have to look this up. What's that? Not what I want. Let's all right. I will have to look it up apparently. there. Yeah, that should be it. Why is that not working? Oh, oh, that, sorry. Yeah. Thank you, Copilot. All right, so it is, the list is yeah, I forgot. But the list is the naming, the namespace, and then iterator is the name of the variable. So this is an iterator into a list of student objects. And then I can do things like equals stu list. Yeah. So there we go. Copilot is being very helpful. So stu list dot begin. So this grabs me an iterator that points at the beginning of my list. And then I can do things like write a for loop. So for, yes. So in my for loop, I can say iter equals stu list dot begin, which is similar to, any other for loop we write with integers. Iter is not equal to stu list dot end. So this loop keeps looping until we reach stu list dot end, and then it exits. And then I have this iter plus plus, which really should be this. So I can increment this iterator, and it's just going to point to the next element in my list. Then when I print it out, I dereference it just like I would with a pointer, and it's going to return a student object that's going to get printed. So let's try that out. Okay, so I added all these students to my list, and then I printed them out using the iterators. Okay, and very, very similar to a syntactically to a regular for loop. But really what's happening is this. So I have my linked list, right? And maybe I have, it's a doubly linked list. And I have a bunch of things in it. And then at the end, well, there's probably a dummy node, but let's just say we have a pointer to null, and then we have our head. So we'll treat it like a classic linked list. When I call this list dot begin, this gives me an iterator that points to the first element in the list. And when I call list dot end, so this one I can dereference, right? This is an iterator. I can store it in an iterator variable, and I can dereference it, and it will return whatever value is stored here. Let's say it's A. So this, if I dereference it, gives me back A. List.end points to just past the last element, right? So it doesn't actually point at anything. This is, it's sort of a points to null, let's say. So that means if I dereference this, I get some sort of error. I forget exactly which one. So this is a valid reference, let's say. List.end is not. It's just an end of list demarcation. Okay. All right, questions? Okay. And you can see that here we keep going until this returns true, which means that now iter is not pointing at anything useful. So if I tried to run this piece of code here, it would not work, right? So I can say do list.end. Okay, so and I get a segmentation fault because I've accessed memory that I'm not supposed to. I'm treating this like a student, but it's actually just a piece of pointing to null or some dead memory or something. Okay. Yes, in addition to this, so we have a regular iterator. We can make this a const iterator. So maybe I want to access my students, but I don't want to be able to change them, right? So if I did something like, what can my students do? So I have a set name function that's not a const function. So if I go to in here, I can do something like, actually, I think I can do this. Iter. Yeah, let's set name to John. Okay, so here it's saying I can't do this because, well, basically because this is not a const function. If I just switch this to a regular iterator, then I can change everybody's name to John using this pointer syntax. But when I do const iterator, it does not let me do that. I do have a print GPA that is const, so I can, since this is now treating it like a const object, I can call the print GPA because it's a const function. So I can do and then, yeah, each of their GPAs got printed out as well as the student themselves. This still works because in my student class, I passed a const student reference. So the output stream operator still works. Yeah. All right, questions? Okay, I can also do something a little bit different. Let's do, now you don't need to use a reverse iterator. And now this is, of course, not working. So let's change this to our iterator. So there are ways to walk through my list in reverse, not using a reverse iterator, but if I forget how, I can simply ask it to do it for me. But now when I ask for stu_list begin, this is a forward iterator, which will not work. So I want to call our begin, which returns a reverse iterator. And our end and our iter. Okay, so before it was Matilda, Joe, Stanley, and Amy, and now it's Amy, Stanley, Joe, and Matilda. And yeah, but you have to explicitly ask for reversed iterators here. And in this case, well, it looks like I'm also using a const reverse iterator. It doesn't have to be const, but I did that in this case. And yeah, if you're wondering, well, can I just use a regular iterator and start at the end and walk to the front? Absolutely. You don't have to use this. We did something like, instead of begin, we want end, but it has to be, end doesn't point to anything useful. So we want to decrement the end, right? Because as we talked about, end points just past the last element. So if we decrement it 1, now it's pointing at the last element. We want to stop. This is a little bit tougher, eh? I'm not sure if it'll let me do this. Not equal to, again, we want to, yeah, maybe. Oh, yeah, it worked. So yeah, I can print them out in reverse just by, paying close attention to the fact that stulist.end doesn't reference anything and stulist.begin does. But I can make a couple small adjustments and just run it in reverse. All right. Questions? Okay. Okay, so yeah, begin, end, dereferencing end will produce a seg fault. Here's a bunch of, reminders of stuff we just did in case you were wondering about the syntax. So those are basic iterators. There are different categories of iterators that we work with. So there are input-output iterators, which work only for input-output streams. So they're very limited in the things they can do. We have forward iterators that only work on containers in the forward direction, which is, you might think, well, how useful is that? But, right, if I have a stream is in some sense only going to use a forward iterator on a certain stream, right? If I'm reading bits from the internet and then throwing them away after, then I can only move in one direction on that stream. However, there are other containers that have bidirectional iterators, so I can walk forward and backwards, as we saw we did with the list. We could increment it and decrement it. And then there's random access iterators, which have direct access to any element similar to arrays, right? So vectors have random access iterators, and we can do pointer arithmetic with them as well. So we can do something like dot begin +2 to start at the, the third most element in my vector. So each of these categories contains all the abilities of those above them. And they're all syntactically the same, except for certain operations are allowed and certain ones are not. All right, so different container implementations have strengths and weaknesses, and the category of iterator sort of reflects that, right? So list, we have this, we can use ++ on list and -, but we can't use the subscript operator. Vector has the most powerful iterators. They can do basically anything. Input, output. Yeah, so I can have an iterator wrapped around cout and cin, and they only use certain actions, as we'll see in a second. And these categories also determine what algorithms can be used, as we will also see. So all iterators support dereferencing, so I can get to, the underlying value or object. The increment operator, I can assign them a value, right? So I can, my iter variable, I can assign it a different value. I can compare it for equality and inequality. These are, operations that I need for a for loop. Yeah. So forward bidirectional random access support dot begin, dot end, and the increment operator. Bidirectional and random access also support the reverse iterators and the decrement operator. So we can, walk backwards and forwards. And then for random access, we also get the subscript, and we get these operators, right? So now we can compare them. It makes sense to say, is this less than this? I can answer that. It makes sense to add an index to my iterator or subtract an index. So yeah, for optimal performance, we want to use prefix, increment, and decrement. Oh, we didn't see that, eh? Maybe we'll get to that on Wednesday. But yeah, they are slightly more efficient. And, the for loop that we wrote here is not really the best, because this line gets executed every loop, and every loop I'm calling this dot begin function, or usually a dot end function, but it's an extra function call, whereas I can just store this, right, and then reuse it. Yeah. Okay. So much stuff. All right. Questions on iterator so far? Okay. We'll get to some more examples in a second. So yeah, sort of, marching alongside these iterators are the types of containers they operate on, right? So our sequence, associative, and container adapters. So all containers provide a default constructor, a copy constructor, a destructor. Remember though, this is shallow. Right? The destructor is also shallow. So if you want to implement deep copies, you have to do that yourself. You also have insert, delete, clear functions. And in fact, there's many overloaded functions. Size related functions. Is it empty? Is it, what's the max size, etc. And the relationship operators. So if I compare two lists, for instance, I can say which one is less than the other. It's just going to go through, it's basically lexicographical is similar to alphabetical order, right? So if I have a list of items and or two lists and I want to compare them, well, if I compare them, what it'll do is it'll look at the first one and it'll say, if one is less than the other, then that list is less than the other list. If they're equal, it will go to the next. We'll compare the next ones. And same thing, if the second one is less than the first one, then that's less than. If those are not equal, it just keeps going down until it finds a difference, right? And that's the same thing we do with alphabetical order. I can say, also and almost, right? So almost comes before also, but you don't figure that out until you compare the S and the M. So the A and the L are the same. That's alphabetical and lexicographical are similar that way. All right. Yeah. So if I want to use my classes in a container, you should provide a copy constructor, assignment operator, or at least make sure that the default ones are sufficient. It is helpful to overload the equals and less than. It's not strictly necessary, but by default, if I want to find something, it uses the equals. And if I want to sort something, it uses the less than. So if I overload those, I maybe save myself a step. All right, so let's look at enough of listening to me talk. Let's look at some input output stream operators. So what we're going to do is we're going to take our nice elegant C out and C in, and we're going to ruin it. So so I can declare an output stream iterator. It's a templated iterator. Again, I'm going to read in strings, and I'm going to pass it as an argument cout, so the standard output stream. And then we can do stuff like this. I can dereference my output stream iterator and assign it this string. So let's take a look at what happens there. All right, so it prints hello there to the standard output, to cout. I have to use here the new line character because unfortunately I can't do this. So even though I could send end line to the cout with the iterators, it does not work. It's only looking for strings because end line is not a string, basically, right? So this is an output stream iterator on strings. I can do, so yeah, enter 2 words. So let's see what happens there. Okay, so hello there, enter 2 words. And in between, I have this plus plus out iterator. However, and the compiler is perfectly happy to let me do that, but it doesn't change a thing about my output, right? So this output stream iterator advances itself by itself. I don't need to advance it. This does nothing. I'm guessing this is also, oh no, it doesn't like that. Yeah, so this one does, it only has a plus plus operator, but that plus plus operator doesn't do anything. I can also declare an input stream iterator, basically the same thing. I'm going to pass C into that. And then what I'm going to do is declare 2 strings, word1 and word2. And word1 is going to take the first value on my input stream, and word2 is going to take the second value. Yeah, let's just start with word1. So enter 2 words, hi there, and my first word was hi. And then I can try and grab the second word off of there. And it says my second word was hi. So unlike the output stream iterator that does not need to be advanced, for my input stream iterator, if I want to grab the second word, I actually have to advance it using the plus plus operator. All right, so this takes this, nice, beautiful input stream and output stream and the stream insertion and extraction operators, which I really like and think are elegant, and make this ugly mockery of them. It is useful for doing things like reading or writing to files, and there are uses for it. This I find really clunky, and I'm not sure why you would do it if you didn't have to, but it can be done. All right, questions? Alrighty. In addition to that, so I'm going to do the same basic thing here, but now I'm going to introduce a vector of strings, string objects. So I'm going to read in. So here I give the instructions to enter words ending with the word end. And then I'm going to, I have my input stream here. I'm going to read in the first word and say, while that is not equal to end, I'm going to push that word on the back of my vector. I'm going to advance my input stream, and I'm going to read the next word off of the input stream. Okay, so let's, we'll get to this in a second. So that puts everything on my, yeah, all right. So we're just going to spit the words back out for now, and then we'll look at this copy function. Enter words ending with N. So hi there, how are you? And so my words are hi there, how are you? So it kept reading until I hit end. I can, hi there, how are you? And I am fine. And it keeps reading until it catches to end, and then it does not read the rest of these. So these are still sitting on my my input stream iterator. But the other thing I can do is use this copy function, which is works with containers in my standard template library. So what it's going to do is it's going to, well, it takes a starting iterator and an ending iterator and an iterator that's going to be written to. So this is the output stream iterator, and it's going to start at the beginning of the vector and to the end of the vector, and simply copy those onto the output stream. Words are, hi there, how are you? You'll notice there's no spaces, so that's, not ideal, but so yeah, this just copies. And again, it's operating on iterators. So we're using it here in this specific instance, but you can use it in a variety of places where iterators, you grab iterators from different data structures and copy them. Okay. So that looks kind of awkward, and we can, artificially introduce, right? When I'm reading it in, I can push a space in between each of them if I wanted to. That would work. But I can also, as a second argument for my output stream iterator, I can add a space here, right? And this will just, now this will be a delimiter on the things that are written to my output stream. So every time it writes one, it writes the delimiter, and then it writes the next one, and then it writes the delimiter, and so on. And I can even use fancy looking delimiters. Right, and now it separates them each by a space with a star. All right. Questions? No. All right. So yeah, those are input and output streams and the iterators that we can wrap them in, and basics on how to use them. And yeah, this is all review on the stuff that we looked at. All right, so these are the main sequence containers we're going to look at. We might skip the deck, but vector and list for sure. Things we can do with vectors and iterators. We got about 15 minutes left. So yeah, the nice thing about the vector is it is an array-based data structure, which means we get random access, which means we get random access iterators. This is all a review of stuff we've already taken. The disadvantage to the fact that it's all packed into an array is that if I insert at the back, it's very efficient. If I want to insert somewhere that's not at the back, as we're going to see, we can do that with the iterators. But then all the elements have to get copied over, right? So if I have an array, A, B, C, E, and I want to insert D, right? Well, let's say I insert D here, then I'm going to have to copy E over here, and I, have to copy C over here and to make room for D. So, it is, it keeps track of the order, but when we insert something in the middle, it's maybe less efficient. Okay, so let's take a look at some of the things we can do with vector. Is that right? Okay, so this is basically, yeah, we're doing things a little bit differently. So this is similar to what we did before. We're declaring a vector of strings. We're declaring an output stream. We're entering a bunch of words into our input stream iterator. But now we're just going to access it directly instead of having an intermediate string variable that we store the result in. So we'll just say, well, as long as this is not equal to end, we're going to push the current word onto our vector, and we're going to advance our input stream. And then we can do as we did before, use this copy function and copy all of these words to the output stream. There. Okay. So everything works as expected. We can look at the capacity of words one when we do that. Of course, we already sort of know if we put 3 things on our vector, it's going to have size 4 because it's at 1 and then doubles every time, or it starts at 0 and then doubles every time. But what we can do is we can declare a second vector called words2. We're going to pass in the size of words1 as a initial value. And what that's going to do is it's going to set the capacity. So it's going to set the backing array for words2 to the size of words1. So however many elements are in words1, that's how big the backing array is going to be on words2. And we'll look at the capacity here. And then we're going to copy everything from words1 into words2 starting at the beginning. Okay, so this is the same copy function we use to copy things to the output iterator, but now we're passing in an iterator to the beginning of a vector. Okay, so we have 5 words, A, B, C, D, and E. So the capacity of words1 is 8. The capacity of words2 is 5 because we initialized it to the size of 5, and then we copied those into words2. I forgot to print them. So let's print them. Okay, so copying, outputting words2. Now words2 has a copy of words1. Of course, the size was initialized to 5. If I leave that part out, words2 will get initialized to 0. Right, and then we get a segmentation fault when we try and copy into it. So the copy algorithm does not automatically grow the vector for us. There is an exception to that. We can use this back inserter function. So instead of copying it just using words2.begin, this back inserter returns a special iterator that adds things to the back of our words2 vector, and then it will grow as needed in this case. Okay, so in this case, it grew as needed. Okay. Questions? No. Words1.insert, we can insert yeah, so we're going to, starting at the 3rd location of words1, we're going to insert everything from words2, which is basically just a copy of things we inserted into words1, but yeah, we can do that using this insert function. So we're copying words1 to words2, and we get this. Seems like a lot. Oh, I didn't print it out. we go. Thank you, Copilot. So yeah. Yeah, so it inserted words 2, which is here, into words 1 in the third location. So we have A, B, C, and C here. All right, so we can also call the erase. And again, we're using, because this is random access, we can use this pointer arithmetic, right? So I'm going to take words 1, I'm going to erase everything starting in the third location up to the fourth location. So, and then output it again. Outputting words 1, yeah. So I didn't really read it very well. All right, so outputting words 1 again, I erased everything from here up to here. Right, so I erased A and B using this just some pointer arithmetic. All right, question. Okay. All right, I'm going to jump right to the algorithms. So there's a bunch of stuff we could cover, but this stuff is directly related to tutorial 10. So we'll just cover this really quickly so you have all the tools, and then next class we'll, I don't know, maybe clean up, cover a few of the things that didn't get to that I wanted to, but otherwise mostly we'll be talking about the final. But yeah, so there is a whole host of algorithms. You've seen a few so far. Some of the algorithms are attached to the containers themselves. So in the previous example, we saw words1.insert. So the insert function is a function for the vector class and not from the algorithms library. But in this case, the copy is from the algorithms library, right? So, but the algorithm also has a whole bunch of other stuff that we can use. So we're going to make, again, 4 students. We're going to have a vector of students. We're going to push the students onto the vector, print them out, but then we're going to call this sort function. And then we're going to print them out again. Let me just... Okay, so here we have the students before sorting. These are just the order we added them in. And then after sorted, we could see they're in, it looks like alphabetical order. And this is sort, which takes, again, it takes iterators as arguments. So this does not necessarily, I probably can't sort a list like this, but I can sort a vector like this. And how does it sort? Alphabetical order. And why alphabetical order? Well, if we look at our student class, we've overloaded a bunch of operators. And in particular, we overloaded the less than operator somewhere. Yeah, right here. Which says sort them in order by their name. So let's say, well, maybe let's sort them in order by GPA. So now it'll be GPA from lowest to highest. And we can see, yeah, so now it's Stanley's got the lowest GPA, Joe's got the next lowest, Matilda's got the next. So we can change this. By default, sorting operation uses the less than operator as defined on your class. If I didn't have that, it wouldn't compile, which I could show you, but we're running a little low on time. The other thing you can do is I can pass in a function. So here I'm passing in a function from the student class, and I'm going to say, well, I'm just going to define any old function. Where did I define it? Oh, I think over here maybe. Yeah, so I defined a static function on the student class that takes 2 students as arguments. And then again, I'm sorting a GPA, but now it's in order by highest to lowest. So yeah, I'm going to sort using this, passing in a function as an argument. But now the GPA is sorted highest to lowest, right? So here I took a static function from my student class, but I can pass any function that matches, that compares 2 students and returns a Boolean, right? So for instance, no, I don't have an example here. But yeah, I can write a global function that compares 2 students in any way I want. I can make it a friend to my student class, and then I can sort using that function on any of the any way that I like. Right. So yeah, and that's basically the for everything in the algorithms library sort of operates like this. It takes a starting iterator, an ending iterator, and then it has some default function sometimes, but other times you're going to supply a function that says how this operates. All right. So I'll quickly show you a few more. So there's a bunch. If you Google standard template library, algorithms library, it will give you all of these things. Here I have an all of function. Again, I have a beginning vector, an ending vector, and then I pass in this pass function, which is a global function that takes a student and returns true or false. So if that student has a GPA greater than or equal to 6, then they pass. And if all of the students pass, this returns true, and I print out all the students have passed. Otherwise, it returns false. If I had to guess, though, it looks like Stanley's failing. So the message is somebody is failing because Stanley's under the bar here. But if I wanted to say, well, don't look at Stanley, just start at the beginning and go to the end -1 so that we'll sweep Stanley under the carpet. Then all students pass because, we didn't look at Stanley. There's also a similar function called any of. So if any of the students are passing, it's going to return true and then print out somebody's passing. So somebody is passing. So this, yeah, I'm printing all the GPAs. Let's not do that. What is this? Print GPA. So again, this takes a student. It's a friend of my student class. The function prints the GPA. And all it does is, of course, print the GPA. And what it's going to do is it's going to apply that function to everybody in this, from the studvec.begin to studvec.end. Right, so here's all the GPAs without the names attached. And there is a find. So this might actually be something you need for the 10th tutorial. So I declare an iterator. This find function returns an iterator. So it looks from studvec.begin to studvec.end. And if any student equals Joe, then it returns that student. So what does it mean to be equal to Joe? Well, I've defined on my student class the double equals operator on a string. So it's going to say, does this student equal Joe? And if this returns true, then it'll return that student and I think print it out. Did we find Joe? So if it doesn't find Joe, it's going to return stuvec.end, which is not, we can't dereference it. Sort of like a null pointer. So did we find Joe? Yes, we did. Joe is right here. We could also have passed in a student, because students can, of course, be compared to other students, et cetera, et cetera. And I think that should give you a pretty good idea of how to use these algorithms for tutorial 10, which are, I forget which ones I asked you. I'm sure sort in there and a find. There might be some other one. All right, so that's it for today. And so next class, I might finish off a little bit of this, and then we will go have a study session. I will go over the practice exam, in particular, the programming part. We'll talk about how all these, because it's more complicated than the midterm. So we'll talk about how they work together. The final exam will be very, very similar. There won't be any surprises. So yeah, if you study the programming part and know how to write all those functions, you'll do well in the final. There's some multiple choice as well, which are a little bit trickier, but if you pass the programming part, I'm happy to pass you. All right, but that's it for today. I can stick around to answer any questions you have, but otherwise I will see you guys on Wednesday.